there, my name's Hannah Hypothesis. I'm helping out with some of the experiments in this MOOC since I'm passionate about aerospace structures and materials and have always been curious to know how things work and why. For each experiment, we'll come up with a hypothesis together for a question we have, then design and perform an experiment to test it. So let's get started. When I was little and starting to think of my first hypotheses, I loved playing with one of these. I spent hours trying to make it walk down the stairs, wondering how it could do that. What I learned is that the toy spring could stretch a lot when I pulled it apart, and when I squeezed it, it became shorter. Then I began to see springs all over the place. Mattresses, car suspensions, and even smaller objects like ballpoint pens and some types of scales all use springs. So this got me thinking, if so many objects rely on springs to function correctly, there must be a relationship that engineers can use to design them. Is there a relationship between the force exerted on a spring and how much it deforms? And what would that even look like? Well, I'm not called Hannah Hypothesis for nothing. This is my hypothesis board. All my experiments begin here, because how are we going to find answers if we don't even have a question? Before we spring into action, let's review what a hypothesis is. Science is all about asking questions, and a hypothesis is a possible answer to a question we have. It doesn't necessarily have to be the correct answer, that's what the experiment is for. But a hypothesis should be testable, and the experiment we conduct should be able to prove or disprove the statement. So let's try and form our spring hypothesis. I think there is a relationship between load and deformation. Therefore, I will make the following hypothesis. A relationship exists between the force we exert on the spring and the deformation that occurs as a result. Now that we have our hypothesis, we'll need to design an experiment to put it to the test. The easiest way to test a hypothesis about a spring is to use, well, a spring. I could just pull it or compress it, but I'm not very good at telling how much force I'm exerting on the spring, so we wouldn't have quantifiable results. Instead, let's use weights of different sizes so we know exactly how much force is applied to the spring. At the same time, we can measure the length of the spring as it deforms under the applied weight. We can then plot that data in a graph and see if there's a relationship. Plotting data in graphs is a good way to find out if a relationship exists. Can we draw a straight line through all of our data points, or a curved line? What is the direction of that line? Does it go up or does it go down? These questions can help us understand the relationship, but that's only good if we have some data. So let's get started with testing. Here we have a simple spring scale. You can place weight on the hook at the bottom of the scale, which deforms the spring inside the plastic tube. The tube has markings for force, so the weight of the object corresponds to where a disc at the top of the spring settles in after loading. This particular scale can hold up to 250 grams, or 2.5 newtons. We also have some weights of different sizes for measuring. There's just one more thing we need, a ruler. You can read out the value for the weight, but since we want to determine if there's a relationship between load and deformation, we'll use the ruler to measure how much the spring elongates under an applied load. And of course, a pen and paper are always useful for writing down our results. The first thing to do is have a measurement we can compare our deformation data points to. As you can see, the scale reads 0 newtons, so there's no weight on it yet. Therefore, I'll take a quick first measurement of where the top of the hook falls on the ruler. It is at 395 millimeters, which is now our baseline measurement. I'll plot our data points as we go so we can see how the data evolves with load P on the vertical axis and spring elongation X on the horizontal axis. Now let's add our first load, 0.5 newtons. The tip of the hook is now at 405 millimeters, and based on our initial measurement, the spring has elongated 10 millimeters. The next weight brings us to 1 newton, and now the spring has deformed to 417 millimeters, or a total deformation of 22 millimeters. Now let's add a few more weights. Now we're at 1.7 newtons, and our ruler is down to 430 millimeters, giving an elongation of 35 millimeters. Starting to see a bit of a pattern? We'll take one more data point. The last weight brings us up to a total of 2.3 newtons. Reading the ruler, we measure a total deformation of 47 millimeters, or 442 millimeters on the ruler. Now that we have all the data, we can start to do some analysis. We can see that the 5 points appear to lie on a straight line, steadily increasing upwards. This gives us a clue as to what the equation that describes the relationship might look like. So what are we able to conclude from our experiment? Well, we hypothesized that there is a relationship between load P and the spring elongation x. Based on the data we took, we can conclude that there is indeed a relationship between these values and that it is linear. There is even an equation to describe this correlation. P, the load, is equal to K times X, the spring elongation. And here, K is the spring constant, a value describing the stiffness of the spring. With this, the behavior of springs can be reliably predicted. Engineers have used this principle in designing systems containing springs, such as oxygen tubes in spacesuits and aircraft landing gears. Maybe one day you'll use these relationships and equations to design a spring system of your own.